So good morning. In the last class, we had started with chapter number 4, which was lattice vibration. I'll quickly take you through this. The first thing we saw there was the potential energy versus the interatomic distances. And we discussed about the potential energy being a minimum. Basically, I wanted to tell you that, when you have lattices and ions sitting there, there is a potential energy. That was the idea. And at the bond length, the potential energy is a minimum. Then, of course, the bond length, you can also talk in terms of the force. You can see that the force is zero at the bond length. That is an equilibrium position. And then we have seen that the properties of materials will be essentially decided by two factors. One is the motion of electrons and their interaction with the lattices. That is one type of properties. The second will be decided by the vibrational motion of the lattices. And we have seen some examples of both these kinds also. Then I asked you to remember what happens if there are some lattice points. Then the lattices, the ions sitting at the lattice will not be sitting at rest, they will be vibrating, we have seen. And why are they vibrating? They are vibrating simply because they have thermal energy. And these small vibrations, you should assume that these amplitude of vibrations will be very small. Let us say it is x much less than a. And what is a? A is the interlattice spacing. Okay, then I talked about the ball and spring model. So you can assume that the ions or the atoms sitting at these positions behave like balls connected by the springs. So what are these springs? The springs are basically the bonds. Okay, and this bond length can be A, which is equilibrium, or they can vibrate so that the bond length becomes larger or smaller. Okay, so we at the end of the class, what we decided was that because the displacement from equilibrium is going to be very small, you can assume that it obeys Hooke's law. And Hooke's law was the spring force or the restoring force is equal to minus kx. Then I also reminded you about the potential energy versus distance graph for any system that obeys Hooke's law. We have seen that the equation for potential energy is half kx square. And we have also seen the restoring force versus displacement. So basically, we just tried to recall a lot of things from the past. And then we came to our lattices. I gave you some 3 lattice points, 3 ions, 1, 2, and 3, connected by these model springs. And then we have seen that this 2 is in the potential well created by 1 and 3. We have already seen there is a potential energy involved, okay? And the shape of the potential energy is parabolic. So you can imagine 2 such parabolics combining together and forming a well like this. So what happens is your atom or ion located here, number 2, will oscillate in such a way that the amplitude of oscillation will be some delta A, where delta A is much less than A. And what is A? A is the interlattice spacing, or the interatomic spacing is A. And we have seen that whenever this kind of a displacement happens, there is a change in potential energy, which is half F delta A square. Please remember this F that we are writing here is the spring constant. This book writes spring constant K as F. And delta A is the displacement. Or basically, we are just asking you to remember the equation potential energy is equal to half kx square, where k is your spring constant F in the book and your x is your delta A. So this is the equation. And because it's a displacement from 0, you can call this as a small change in potential energy delta U. Okay. Now, after that, I talked about longitudinal and transverse. I said that these displacements of any atom or ion is not independent of what is happening around it. It's an orchestrated motion because after all, each of these atoms are connected to each other by these bonds. Then I also gave you some points in support of the ball spring method. So this is where we start. So today let's start off with normal modes. We will take a very simple model that will be a one-dimensional monoatomic chain. You know that no material is one-dimensional, but then we are going to just consider as our example a one-dimensional chain. Okay, so this is our chain. You have an ion sitting here, atom or ion sitting here, 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 here. So this is our chain. Okay, it's one-dimensional. And what is the interdistance? The distance between them is A. A is the distance. And let us say that there are n identical atoms or ions. N identical atoms or so it's long. And what is the length of the chain? The length of the chain will be, anyone? A is the distance between the atoms and n number of atoms are there in this crystal, in this monoatomic one-dimensional crystal. So what will be the length of the chain? A is the distance. So if I have like this, if I keep taking n such atoms or ions placed in a line, then the length will be n into n into A. Okay. So now what we'll do is we are assuming that it is monoatomic. Monoatomic means made up of one type of atom only, one type of atom, one element. Okay. And further we are going to say this chain as n primitive cells. We are going to treat each of this atom as a primitive cell. Okay. Now each of this atom is taken as a primitive cell. And another thing that we are going to do, another assumption is that we will consider only nearest neighbor interaction. We consider only nearest neighbor interaction and pretend as if the other fellows are not affecting this guy. Let us say I will call this as lattice position L. So the atom or ion sitting at the lattice position L will be affected by the guy sitting at L minus A and the guy sitting at L plus A. So these two are the immediate neighbors for the atom sitting at L. So we pretend that L minus 2A, this guy will be L minus 2A. The guy sitting at L minus 2A and the guy sitting at L plus 2A have very little influence on L. So this is what is called the nearest neighbor interaction. This is not true, but then we are going to assume that only nearest neighbor interactions are appreciable and far off atoms don't really matter. Okay, and end atoms, of course, don't really matter at all. Next, we will just use our harmonic approximation. And already I told you, these atoms will not be sitting in their positions. Because of thermal energy, they are going to vibrate. So look at the next picture. There is a screenshot. Okay, in this shot, you are seeing that the atom here has moved through a distance. This is the second picture of the chain only. So it has moved through a displacement SL minus A. This guy has moved a displacement SL. This one is SL plus A. This is SL plus 2A. So like this, no, the displacement away from the equilibrium, these were the equilibrium positions. The displacement away from equilibrium positions, let us consider. So if there is a displacement away from equilibrium position, already we have seen in the last class that if I take two atoms like this, then there is a potential energy. We already saw that the potential energy is given by minus Ka, and change in potential energy, half Ka square. And change in potential energy is going to be half K delta A square. We have already seen that in the last class. So now what we'll do is, we will talk about, this is for a two body. Okay, now let us consider three atoms. Let us consider three atoms. L is our hero, and then to the left and to the right. Let us take these two. And we will talk about an effective potential energy for this chain by just considering. So what we'll first do is, we will not even do this. Let us just consider L and L plus A. Let us just take L and L plus A, talk about this bond length and change in the bond length, and then use this equation and talk about the potential energy. So the potential energy, effective potential energy, okay, is going to be half F SL minus SL plus A whole square. Comes from here. Half F SL minus SL plus A whole square. What is this SL and SL plus A? They are the displacements. They are the displacements. So when you do SL minus SL plus A, you get the net displacement. You get the net displacement. This distance is going to be A plus some net displacement. Okay, so I get the net displacement by just taking the difference of SL and SL plus A, and then of course I am squaring it. But then I want for the entire chain of N ions or atoms. I want for the entire crystal made up of N such atoms or ions. So what should I do? I just have to add each such pair of interaction. I just have to take and add. Okay, so all I will do here is summation L f of SL minus SL plus A whole square. I hope this equation is clear to you. First I write for one pair, L and L plus A. Individually look at the displacement for each of them from their equilibrium position and talk about the net displacement. Okay. Therefore, I am getting an equation for the potential energy of just these two ions as half F into SL minus SL plus A whole square. Now, if I want for the entire chain of N atoms, what should I do? I need to do a summation for each pair, each adjacent pair like this. Is this clear? Yes or no?
Yes, ma'am.
Right. So now that's why that summation has come. And again, I am insisting that we will only consider the nearest neighbor interactions. So now let us write the restoring force equation. You remember restoring force equation the other day I wrote it as minus K into X or delta A. Okay, so we are just going to use this here and let us set up the equation. The restoring force on, now we are talking about the restoring force on an ion, not about the entire chain. We are talking about the restoring force on this ion sitting at lattice Al. Okay, so for doing that, look at the left hand side of this equation. This is going to be mass of the ion. Let capital M be the mass of the ion. And the displacement is ASL. Okay, now if I differentiate it twice with respect to time, I get my acceleration. ds by dt is velocity. D square s by dt square is acceleration. And you know that mass into acceleration is force. Okay, so that's why I'm getting the left hand side. And on the right hand side, what should I do? I have to write K is small f according to this book. And then I have to talk about the displacement considering L, L minus A and L plus A. Nearest neighbor interaction I have to consider. Meaning I have to consider SL minus A, which is the displacement of L minus A, then SL, which is the displacement of the atom at L, and SL plus A, which is the displacement for the atom sitting at L plus A. So I consider the nearest neighbor interactions, okay, and talk about what is the net force on L, and talk about what is the net force on L. So I know that it has got something to do with the distance. So what I do is, first I consider the displacement between L and L plus A, then between L and L minus A, and then add up these two displacements. So I get the net displacement. So the net displacement is proportional to the restoring force. Okay. So it is SL minus SL plus A plus SL minus SL minus A. Basically, I'm considering both these pairs and talking about the effective displacement here, effective displacement because of this, and adding up both of them. So look at this, SL and SL is repeating twice, so 2 times SL, then of course minus SL plus A, then minus SL minus A. So I get my equation 4.3. Now this equation is important because it is the equation of motion of the ion sitting at the lattice site L. So this describes the equation of motion of this guy considering the two neighbors exerting force on L. Okay, so I write this in terms of the displacements. Now this is a differential equation. Equation 4.3 is a differential equation. And what am I interested in? I am trying to get a solution for SL. What will be the equation that will describe SL, the displacement SL? So without getting into the max of it, if you get the solution is going to have a form SL equal to S naught exponential I K dot L minus omega t. S naught exponential I K dot L minus omega t. So this must be looking familiar to you. What is this equation? This is the equation of a, anyone? Anyone? There's an exponential I K dot L minus omega t. Does this remind you of something? This is the equation of a wave. This is an equation of a wave. Okay, wave. Okay, which can move direction, and S naught is the amplitude. Omega is the frequency, and t is the time. T is the time, omega is the angular frequency, k is the wave vector, which is 2 pi by lambda, and S naught is the amplitude. Or in other words, what is going to happen is this guy, atom sitting at SL, okay, will get pulled on this side effectively. Then because of the stirring force, it gets pulled on this side. So basically, it's going to vibrate. And in vibrating, what it is doing is it is disturbing the neighbor. So this vibration is getting passed on to the next guy. Like I'll give you an example. Sometimes you must have had this experience of sitting in a theater. In a theater, let's say 10 people are sitting. One guy is sitting there and tapping his leg. One guy is sitting there and shaking his chair. So when he does that, won't the fellow sitting next to him also feel the disturbance? Will he feel the disturbance or not?
Yes, ma'am.
Right. What about the second guy? Will he also feel the disturbance?
Yes, ma'am, but lesser than the first
At
one.
least. The 10th fellow will not feel any disturbance. So what is happening here? This guy is sitting here and disturbing, and this disturbance is going to travel as a wave. Okay, and this guy's disturbance is like a oscillation. So what happens is this atom sitting at the nth position, because of thermal energy, oscillates, and because they are all connected by the spring, that model, that spring or the bond, this disturbance gets transmitted as a wave. Okay, next what we'll do is, so we got our solution. So this is our solution, and I actually went one step ahead and told you that the third fellow, fourth fellow, fifth fellow, everybody is going to get disturbed, but then smaller and smaller disturbance. But here we have made an assumption that only the second fellow is going to get disturbed. The zeroth fellow, the first fellow. Only the disturbance will be for the neighbor. So that's what we are right now telling. And now we got our solution, equation 4.4. Take equation 4.4 and put it in equation 4.3. Take 4.4 and put it in equation 4.3. So how will you put it? How will you put it? You know that SL is S naught exponential I K, plus, K dot L minus omega t. Similarly, if I want SL minus A will be S naught exponential I, then K into K dot L minus A, then minus omega t. So similarly, you can write S of L plus A, that will be S naught exponential I K, then I K dot L plus A minus omega t. So put all this into this equation and then solve it. You will find that a lot of terms will cancel out. Okay, you will find that S naught will cancel out, exponential I K dot L minus omega t will get cancelled out. A lot of things will get cancelled out. And let's see what we will get. And each time you're going to do a differentiation. On the left hand side, you're doing a differentiation with respect to time. So you will get an omega square. Here you have omega t, no? So you'll get an omega square on the left hand side. with a capital M, and common terms will get cancelled out. So let's see what we get. All common terms will get cancelled out, and you will be left with capital M omega square is equal to F into 2 minus exponential I K A minus exponential minus I K A. All other terms will get cancelled. Now I want you to answer this question. What is exponential I theta plus exponential I theta? Anyone? Exponential minus I theta. Exponential I theta is cos theta plus I sine theta. Similarly, exponential minus I theta is going to be cos theta minus I sine theta. So minus I sine theta and plus I sine theta will go off. So you get 2 cos theta. This is max. You should be actually teaching me. Okay. So using this logic, okay, we'll have 2 is already there. So 2. And this m I'm getting from this side. I'm getting it here. So f by m. So 2 minus 2 cos ka. So your theta is ka. So 2 cos ka. Is the step clear? Next, what we do is let us take out 2 outside. So 2f by m into 1 minus cos ka. Now, I want you to remember this formula, 1 minus cos 2 theta. What is 1 minus cos 2 theta? Anyone? 1 minus cos 2 theta is sine square theta. Okay, so we are going to just use this. So 2 theta is ka. So ka by 2 is theta. So just use this and you will get omega square is equal to 4f by m. Okay, there is a 2 here. Okay, so 4f by m sine square ka by 2. And what is omega? Omega is the angular frequency of oscillation. So let us get omega from omega square. So omega will be under root of the right hand side, which is under root of right hand side. 1 second. I think I'll do one thing. Pointer. Yeah. So let us use so the angular frequency of oscillation is under root of this right hand side. So it gets 2 under root of f by m and then under root of sine square ka by 2, and we are putting a modulus here. We are putting a modulus here. Why this modulus is coming? This modulus is coming because, and similarly here also under root of 4, we are taking as positive 2. We are taking this positive simply because omega cannot be negative. Omega cannot be negative. Omega has to be positive. Angular frequency cannot be negative. It has to be positive. That's one thing. So we want a sign, can take positive and negative value. We don't want negative. We are taking only positive. Then another thing is you're seeing that from here you're seeing that omega is a function of k. You're seeing that omega is a function of k. Pointer. I want to get rid of pointer now. Okay, I want to get rid of pointer or got rid. Okay. So the angular frequency you're seeing is omega as a function. Omega is a function of k. Option every time I have to do this or what? Yeah. So omega is a function of k. You know what is k? K is your wave vector 2 pi by lambda. So omega is a function of k. How did I get this? I'm getting this because I'm finding that k is the only variable that I'm seeing. F is a property of the bond or the spring. M is mass of the atom. A is the bond length. Therefore, k is the only variable. So omega is a function of k. Now, this equation is going to follow you all your life as long as you're going to do physics. It's a very, very important equation. Okay, and this equation is called the dispersion relation. It's called the dispersion relation. It basically tells you about how energy losses can be there when a wave propagates through a medium. Okay, that's what it's called, the dispersion relation. Next, what we'll do is, I don't know whether you noticed, here I had written 2f, 2 into under root of f by m. Sine will not have any unit. So we will write one extra step here. Omega is a function of k. We can call this constant as omega m, a constant, into sine of ka by 2. We are calling this omega m because the value of omega will be 2f by m, 2 under root f by m, when sine ka by 2 is equal to 1. Okay, so it will have the same unit as omega, so we call it as omega max. So this is the maximum value of omega. So that's why we are writing omega k is equal to omega m into modulus of sine ka by 2. This is called the dispersion relation. And omega m is this. So this is also called the angular frequency maximum. When are you going to see this angular frequency maximum? Let us see when we will see this angular frequency maximum. When your k is going to be plus or minus pi by a. When your k is going to be plus or minus pi a, then what happens? Sine ka will be equal to sine of plus or minus pi. And what is sine of sine? Am I right? So pi by 2. Okay, it will be pi by 2 because it is ka by 2. Okay, so what is sine pi by 2? What is sine pi by 2? God help me. What is sine pi by 2?
Zero.
Huh?
Zero, right?
What is
Sine
sine
pi.
90? Sine 90 is
0 to
1.
1. That's it. So it is 1. Okay, so it can be plus or minus 1. But then we are talking of a modulus. Because we have put a modulus, this is going to be just 1. Okay, so you find that whenever k is equal to plus or minus pi a, at that time omega is going to be equal to omega m. Okay, it shows a maximum omega. Okay, what will k equal to 0? What will happen when k equal to 0? When k equal to 0, let me just write this, omega equal to omega m. Here, when k equal to 0, you're going to see that omega is going to be equal to 0. So this is the minimum value and this is the maximum value. And you're seeing that there is a symmetry, 0 at the center, minus and plus. Okay, so if one were to plot it, if one were to plot this equation, this is how it will look. Dispersion relation. If you plot, what you get is going to be the dispersion curve. This is going to be the dispersion curve. And what are you plotting? You're going to plot k on the x-axis, and then on the y-axis, it's going to be omega as a function of k. And look at this. It is a symmetric. There's really nothing here. It is just a sine curve only, a sine curve. But then if you take a sine curve, because it is modulus, it will come like this. That's all. It will come like this. This guy is not going to be there. And it's not a sine. It's actually modulus of sine. So you get this and this. Okay. So look at this. So you've got this is corresponding to 0k. This corresponds to minus 2 pi by a. And then this corresponds to plus 2 pi by a. This corresponds to plus 2 pi by a. At minus 2 pi by a and plus 2 pi by a also, the function is 0. And when is it a maximum? It's a maximum at, I've already written here, at plus minus pi by a. So this is minus pi by a, and this is plus pi by A. This graph is very important, okay? And if you recall, we did this taking one ion or atom sitting at the nth position. One atom or ion sitting at the nth position. Okay, now if you want to consider the entire atom, the entire crystal of n atoms, you can simply take the same thing, because if you look at the solution, if you look at this equation 4.6, if you look at the equation 4.6, you're going to see that it does not involve L. Equation 4.6 does not involve L. L was the position of the ion or atom sitting at the lattice L. But since L is not there in the equation, okay, you will get a similar solution for each of the ions in this n ion crystal. So we conclude that in an n, they are harmonic oscillators. You call them harmonic oscillators because they are just obeying your Hooke's law. So for the n harmonic oscillators, the solutions that you will get will be n such equations. You will get n such equations, SL equal to S naught exponential I k dot L minus omega t. Like this, you will get n equations. And you're seeing the omega k equation that you got did not involve L. So you can simply say that you will get n uncoupled independent equations. And each of these solutions that you get is called a normal mode. It's a normal mode of vibration. Though it's a coupled oscillator of n connected to each other and coupled, the solution that you got is n uncoupled solutions, and each of the solution is called a normal mode. So we have made a small, we've just taken a small liberty and then presumed that the interaction is not going beyond the neighbors, beyond the nearest neighbor. So what is the meaning of normal mode? Now let us see what is the meaning of normal mode. Normal modes are independent, non-interacting modes obtained using harmonic approximation. So that means this n body problem, n atom, one dimensional crystal has n independent way by which the atoms can vibrate. N independent ways the atoms can vibrate. And you are considering these modes as non-interacting. This is a simplification that we did. Okay, but then you know the system is not like that, it is coupled. So they cannot oscillate independently. We have tried to pretend as if no, the L will oscillate, the L plus 1 will oscillate, each of them will oscillate in the same way and independent of each other. But already we broke that myth in a previous picture that we have shown you. Here, for example, you can see that the vibrations are not going to be independent. Or look at this, the vibrations are not independent. They are linked to each other. It's an orchestrated motion. That's what I keep telling you. It's an orchestrated motion. They are not independent. So we have made a small concession there by pretending that they are independent of each other, not linked to each other. So the system is coupled. It is not uncoupled. It is a coupled system. Therefore, it will not vibrate independently as we think. It will not vibrate independently. So if one ion starts vibrating or atom starts vibrating, it will not keep vibrating with a constant amplitude. You must remember that energy is proportional to the square of the amplitude. So it will not oscillate with a constant amplitude. Some of its energy it passes on to the next fellow vibrates, then the next fellow. So it will not continue to vibrate with a constant amplitude. The energy is transferred to the adjacent neighbors, and the vibration of the individual ions is thus not simple harmonic or uncoupled. We assumed it is simple harmonic and arrived at the normal modes, but then in reality, they cannot vibrate independently. Okay, so now what we have to now say is because they are coupled, you can simply say that superposition of normal modes will represent the actual motion, will represent the actual wave. What is the meaning of superposition? Let us say I have x1, x2, x3, etc. are some solutions for some problem. Then superposition means the solution x will be a1 times x1 plus a2 times x2 plus a3 times x3. This is called superposition. Okay, so we say that yes, you got n normal modes, they are all identical, good for you, keep them there. The actual one, it's not a waste, these n are not going to be wasted. Okay, these solutions or normal modes will superpose on each other and they will add up and give you actual motion of the wave. And what is this wave? Wave is a disturbance. Okay, to understand exactly what is happening here, we have to arrive at periodic boundary condition. So what we will do is, this is something that I already repeated, so I'm not going to say that. So now we have to find out all possible normal modes of frequencies that lie in the k value range minus pi by a to plus pi by a. And if you remember this minus pi by a to plus pi by a, do you remember the word first Brillouin zone? In the previous chapter, we defined something called the first Brillouin zone for a linear monoatomic crystal. There also we took linear monoatomic crystal and we said the first Brillouin zone is lying on the reciprocal lattice line and it lies between minus pi by a and plus pi by a. So that's your first Brillouin zone. So here also this minus pi by a to plus pi by a is the Brillouin zone. So within a first Brillouin zone, you are seeing a variation of omega as a function of k. Okay. And to obtain the complete spectrum of the normal modes, okay, we have to use the periodic boundary condition. So for that, what we'll do is, we will take this chain which is having a length n a. We will take this entire chain having this n atoms or ions. It's a linear chain. Now just connect both these ends. Connect both these ends so that you get a ring. Connect both these so that you get a ring. Now the length of the ring will be L equal to N into A. Capital L equal to N into A. Only thing is it is a ring. Okay. Now let us take one atom here. One atom or ion here. Let its position be PA, where P is an integer. Let its position, because L, we use small l and said lattice L, atom sitting at lattice L. Like that we'll say PA is denoting this particular atom or ion. Now, what will be PA plus Na? Anyone? Which will be the ion or atom represented by Pa plus Na, where N is the total number of atoms or ions in the chain. I talk about the location. Once more, I repeat, I talk about the location of this ion or atom as Pa. From some origin, I move P steps, I move a length Pa and reach here. Now, what will be Pa plus Na? This is my ring. Can you see my bangle?
Yes, ma'am.
Right. Let's say the total length of this is capital L and it has got capital N number of ions or atoms. I take randomly one atom here. With respect to some origin, I'm saying that I have to travel P steps and a distance Pa. So I will call this position as Pa. Now what I'm asking is, what will be the atom represented by Pa plus Na? That means from Pa, I have to move a distance capital Na. If I move a distance capital Na, where will I reach? How many atoms are there in the chain, in that ring? How many atoms are there in that ring? I said capital N number of atoms are there. And what is the distance between the atoms? The distance between the atoms is A. So if I move through a distance capital N into A, where will I reach? I will come around once and I will reach the point Pa. I will come around once and reach the point Pa. So I can simply say that the position given by Pa plus Na is actually Pa only. It is Pa only. So we are just going to use uh, this and write that the displacement of the lattice L, atom sitting at lattice L, is the same as displacement of the lattice L plus Na, because after all, L plus Na is L only. Okay? And if I say that L equal to some, small l equal to some Pa, where P is some integer, and capital Na is capital L, the length of the string. Okay, then I can say that S of L is S of L plus Na, or there is a periodicity. Okay, so we are just using this periodicity, and you are also taking this normal mode equation. Okay, and using this, what will I get? I will get S of L equal to S naught exponential I k dot L minus omega t is equal to S naught exponential of I k dot L plus Na minus omega t. So from this, what I will get is exponential I k l is going to k small l will be equal to exponential I k into L plus Na. Okay, so this is what I will get. Okay, now what does this mean? This means this is equal to exponential of IKL into exponential of IKNA. IKNA. And on the left hand side, I have exponential of IKL. So this implies exponential of IKNA equal to 1. Exponential of IKNA equal to 1. Okay. And you know that 1 can be written in the exponential form as exponential I 2 pi n, some small n, where n is an integer. I can write 1, you know that exponential I 2 pi n is 1. Okay, so what I will do is, we will write exponential ik capital Na is equal to exponential I 2 pi small n, where small n is some random integer. So now you can just equate these two and arrive at an equation k into capital Na equal to 2 pi small n, or I get k equal to 2 pi small n divided by capital Na, which is n into 2 pi divided by capital L. N into 2 pi divided by capital L. Capital L is capital N into A. Capital N is the number of atoms or ions. So this is an important equation. This gives me all possible case. This gives me all possible values of case. Case can take only discrete values and all allowed values of K. And where is it? So all the allowed values of K, where n equal to 0, plus 1 minus 1, plus 2 minus 2, all this is possible. Plus 1 minus 1, plus 2 minus 2 is possible simply because K can take negative values. Now, We want to confine ourselves to the first Brillouin zone starting from minus pi by a to plus pi by a. Okay, now let us see how many k's are going to be possible between these two limits in the first Brillouin zone. Okay, so now what do? Just keep putting small n equal to 0, plus 1, minus 1. Just keep doing that. When you do that, you will get k equal to 0, plus minus 2 pi by capital L, plus minus 2 into 2 pi by capital L. Keep on going. And at some stage, when you put small n equal to capital N by 2, zero all the way to k equal to plus minus pi by a. And how many small n's did you have? Corresponding to small n equal to 0, plus minus 1, you went on till you reach capital N by 2. Plus minus capital N by 2. Or there are n number of k values in the first Brillouin zone. In the first Brillouin zone, capital N number of k values are possible. Capital N number of k values are possible. N can take value capital N by 2, but then because it's plus and minus, you will be seeing that there are n number of values possible. Capital N number of values possible. So these are the possible values of k. Okay, and you've already seen an equation. Omega k is related to this by the equation omega m into modulus of sine ka by 2. Okay, so this also means that there are n omega values in the first Brillouin zone. Okay, so from dispersion relation, you are able to see all the allowed k values and all the allowed omega values. All the allowed k values and all the allowed omega values. Now I have to tell you something. We confined ourselves to 0, minus pi by a, plus pi by a, which is the first Brillouin zone. Now, if you go out of the first Brillouin zone on either side, you will be able to see other k values and omega values, but you will see that because of that sine ka by 2, the omegas that you are getting outside here will not be unique. It will be simply a repetition of what you got inside your first Brillouin zone. Or to study all possible modes of vibration, you need not go all through the crystal. Just take the first Brillouin zone and see how many Ks and how many omegas are possible, how many unique values of Ks and omegas you got when you have studied the entire material. So what I meant was you confine yourself to just this, and within this you found that there were n number of allowed Ks and correspondingly n number of omegas. Outside this, if you go, what you get is simply going to be a repetition only now. So you won't get anything unique outside. So the total number of unique K values, normal modes are capital N. And when k changes by 2 pi by a, 2 pi by a means this entire distance. When k changes by 2 pi by a, then what you get is only a repetition. Look at this. I am getting this. Once I change by 2 pi by, I am getting this. I am here. If I change by 2 pi by a, I am getting this. What I get will be just repetition. All unique values of k satisfying this SL can be obtained by just confining ourselves to the first Brillouin and using the dispersion curve. And what we'll do in the next class is I will start from here. I will start from this point and discuss the salient features of the dispersion curve for an n monoatomic one-dimensional crystal chain. Okay, so with this we stop the class for the day.